Wow, that feels really cold, even if it's just sitting there in a warm room. Or maybe you've noticed how sound seems to travel right through a solid wall, but then get completely stopped by a thick curtain. These everyday things, they seem simple, right? But they actually hint at this fascinating quantum secret buzzing underneath. So today, we're taking a deep dive into the world of phonons. You've given us a fantastic stack of sources here covering everything from the absolute basics to some really cutting-edge applications. Our mission today is to pull out the most important bits of knowledge, the real insights from all this, so you can get up to speed on this really captivating subject pretty quickly. So what are these mysterious quasi-particles, and why are they so essential for understanding, well, everything from how heat flows in your phone to the physics of superconductors? Okay, let's unpack this.
It's actually quite remarkable, isn't it? How the idea of a phonon neatly bridges that huge gap between the microscopic world atoms jiggling around and the macroscopic things we actually see and feel, like temperature and sound. At its heart, a phonon is just a quantum of lattice vibrational energy. Simple as that, conceptually at least.
Okay, so before we jump into the quantum side of things, maybe let's just set the scene a bit. How did we used to think about atoms in a solid? Classically. I mean, for a long time, the picture was this perfect, ordered grid, almost static, right? But that idea started to run into trouble.
Oh, absolutely. That classical view started showing cracks when scientists tried to explain certain observations. The reality is atoms in a solid are never truly still. They're always vibrating, even at room temperature. You can picture them like little masses connected by springs constantly oscillating because of thermal energy. And when one atom moves, it doesn't just move on its own. It bumps into its neighbors, creating this ripple effect, this wave of disturbance that travels through the whole crystal lattice. These collective coordinated movements are what we call normal modes.
Right, that makes sense for how heat or sound could travel. Seems pretty intuitive. But if that classical picture works so well for that, what was the problem? What forced the quantum leap, as you put it?
Well, the classical model hit a major wall with something seemingly basic, the specific heat of solids, especially at very low temperatures. See, the classical de Long-Petit law predicted that the specific heat should be constant, no matter the temperature. But experiments, particularly near absolute zero, showed it dropped off dramatically. The classical model just had no explanation for that. And that's exactly where quantum mechanics stepped in. It was analogous to Planck realizing light energy comes in packets called photons. Physicists realized the energy of these lattice vibrations must also be quantized, come in discrete packets. And this packet of vibrational energy got its name, the phonon. Igor Tamm suggested it back in 1932 from the Greek phone for sound, which fits because long-wavelength phonons really are the microscopic bits of sound waves. And like photons, each phonon has a specific energy, E equals UCO, the Planck-Einstein relation. This totally changed the game from thinking about continuous waves to these discrete particle-like energy packets.
Okay, and this is where it gets really interesting, but maybe a bit confusing too. Is a phonon a real particle, like an electron? Or is it something else? The sources are clear it's a quasi-particle. Can you help us wrap our heads around that?
Yeah, that's a crucial distinction. Think about it trying to track every single atom vibrating in even a tiny grain of sand, which has maybe 1017 nuclei and 1018 electrons. It's just impossible, computationally intractable. A quasi-particle, like the phonon, is what we call an emergent phenomenon. It's essentially a conceptual tool, a useful abstraction. It lets us describe the collective behavior of this incredibly complex system, all those interacting, vibrating atoms, as if it were a single, simpler particle. It simplifies this massive many-body problem so we can actually use statistical mechanics, like Bose-Einstein statistics, to understand and predict how the material behaves overall.
So it's not a fundamental piece of matter itself, but more like a pattern of motion, a collective ripple that emerges from the matter, and it can't exist on its own outside the crystal lattice it's moving through.
Exactly right. The phonon is intrinsically linked to its host medium, the crystal. It needs the lattice to exist. And its whole theoretical beginning, as we mentioned, was driven by that need to explain the specific heat problem. Einstein, back in 1907, took the first quantum crack at it. He modeled the solid as basically n independent oscillators, all vibrating at the same frequency. It was a breakthrough because it did predict specific heat going to zero at low temperatures, but it predicted an exponential drop, which was faster than what was actually measured. So, close, but not quite right. Then Peter Dubé came along in 1912 with a major improvement. He treated the lattice vibrations not as independent things, but as a whole spectrum of collective modes, these phonons propagating through a continuous elastic medium. Sort of like photons in a box. He introduced a key idea, a maximum cutoff frequency, the Dubé frequency. and his model was a huge success. It nailed the T-cube dependence of heat capacity at low temperatures, the famous Devi-T3 law, and it also correctly gave back the classical de Long-Petit result at high temperatures. It was a cornerstone for solid-state physics.
Okay, so we've got photons and phonons, both related to quantization, both have that E-Rudo thing going on, but they're fundamentally different beasts. For someone listening, what are the absolute key differences and why do they matter?
The biggest one is their fundamental nature and where they can exist. A photon is a fundamental particle, the quantum of the electromagnetic field. It can zip through a perfect vacuum. A phonon, though, it's a quasi-particle, a collective excitation of the lattice. It absolutely needs that medium, the crystal, to propagate. No vibrating atoms, no phonons. Simple as that. And another really key difference is momentum and speed. Photons have true momentum and travel at the constant speed of light, c in vacuum. Phonons have something called crystal momentum. It's a bit more subtle. It reflects the underlying periodicity of the crystal. It's conserved in interactions, but in a way that relates back to the repeating lattice structure. And their speed. It's the speed of sound in the material, and crucially, it's often dispersive, meaning it depends on the phonon's frequency and direction. This dispersion is vital for understanding how heat and sound actually move.
Got it. So one's a fundamental particle of light, the other's an emergent ripple within matter. That difference really dictates how they behave and interact, which brings us neatly to the phonon's fingerprint.
Right, the dispersion relation, usually written as LOC. What's fascinating here is that this relationship between the phonon's frequency and its wave vector k is really the central piece of information you get from lattice dynamics calculations. It's genuinely a fundamental fingerprint of a material's vibrations. It tells you about the crystal structure, the masses of the atoms, the forces between them, everything. And it governs the material's acoustic properties, its thermal properties, its elasticity. We usually plot these as dispersion curves, often along specific high symmetry directions in what's called the first Brillouin zone. And for a 3D crystal with our atoms in its basic repeating unit, its primitive cell, you'll always find exactly 3 distinct phonon branches on this plot.
And how fast does the actual vibrational energy travel? That's where group velocity comes in, right?
Yeah.
Vg equals the gradient of mu with respect to k.
Exactly. The group velocity, Vg equals ik-cook, is essentially the slope of that dispersion curve. It tells you the speed at which a wave packet of vibrational energy propagates. Absolutely crucial for understanding heat transport, because phonons are carrying the heat energy.
So faster phonons mean faster heat transfer, generally speaking.
Generally, yes. And here's a neat point. Where the dispersion curve becomes flat, say, at the edges of that Brillouin zone, the slope is 0. The group velocity is 0. Phonons in those states are essentially standing waves. They're vibrating, but they aren't moving energy anywhere. They don't contribute to net heat flow.
Okay. And alongside the dispersion, there's the phonon density of states. What does that tell us?
D quantifies the number of available vibrational modes per unit frequency interval. Think of it as asking, at this specific energy or frequency, how many different ways can the lattice vibrate? It's super important because you need it to calculate macroscopic thermodynamic properties, like the total internal energy or the heat capacity we talked about earlier. You sum over all the modes weighted by this density of states. The Debye model, for instance, gives that simple du proportional to O² approximation at low frequencies, which works remarkably well in many cases.
Now, within those 3 branches you mentioned, there's a key split in crystals with more than 1 atom per unit cell. Acoustic versus optical phonons. 3 acoustic, and the rest 3 are optical. Let's start with acoustic. What makes them acoustic?
Acoustic phonons are defined by the atoms within that basic unit cell moving pretty much in phase of each other. Imagine the whole unit cell moving together, like a tiny piece of the crystal undergoing a collective displacement. Crucially, their frequency goes towards 0 as the wave vector k goes to 0. At long wavelengths, this always-k relationship is linear, just like macroscopic sound waves, hence the name acoustic. You get 1 longitudinal mode, LA, where atoms move parallel to the wave direction, and 2 transverse modes, TA, where they move perpendicular. They typically occupy the lower frequency range, say, below 10 terahertz or so.
Okay, so those are like tiny sound waves propagating. What about the optical phonons then? How are they different?
Optical phonons are quite distinct. In these modes, the atoms within the unit cell move out of phase relative to each other. It's more like an internal vibration within the unit cell, often with the center of mass staying put. A key difference is that optical phonons have a non-zero frequency, even at K0, at the zone center. Their dispersion curves also tend to be flatter, meaning lower group velocities. They're generally less efficient at transporting heat over long distances compared to acoustic phonons.
And why optical? does it relate to light?
Exactly. They got their name because in ionic crystals, think sodium chloride, NaCl, or gallium arsenide, GAAs, these out-of-phase vibrations involve charged ions moving against each other. This creates an oscillating electric dipole, and that dipole interacts very strongly with electromagnetic radiation, specifically with infrared light. So they're optically active, measurable with IR spectroscopy. Like acoustic modes, they come in longitudinal LOA and transverse TO varieties. And in polar crystals, you often see a gap, a splitting, between the LO and TO frequencies due to long-range electric forces. These guys are usually at higher frequencies, maybe above 10 THz.
So putting it all together, this dispersion relation, this third plot, isn't just some abstract graph. It's like a diagnostic fingerprint for the material.
Precisely. If you measure a material's phonon dispersion, you learn so much. The number of branches tells you how complex the unit cell is. The slope of the acoustic branches near KO0 gives you the speed of sound directly. The size of the energy gap between acoustic and optical branches tells you about the strength of the bonds holding the atoms together. That LO-TO splitting we mentioned. It's a direct measure of how ionic the material is, and sometimes you might see a specific phonon mode dramatically decrease in frequency, what we call softening, as you change temperature or pressure. That can actually signal that the crystal lattice is becoming unstable, a precursor to a structural phase transition. It's a really powerful tool.
Okay, now that we have a good feel for phonons themselves, let's connect them back to the everyday properties of materials. We touched on internal energy and specific heat, how the total energy is the sum over all the phonon modes, and specific heat is how that energy changes with temperature. High temps, classical Dulong Petit; low temps, only low-frequency acoustic modes are active, leading to that WT3 law for insulators. That works beautifully. But this raises a really basic question. Why does a solid typically expand when you heat it up? Where does that come from?
That's a great question, and it gets right to the heart of something fundamental we often approximate away. A perfectly harmonic crystal, where the forces between atoms are like perfect springs, actually wouldn't expand at all. The atoms would vibrate more, sure, but the oscillations would be perfectly symmetric around their average positions. Real interatomic potentials, however, are anharmonic. They're not perfect quadratic wells, there are higher-order terms. And it's the asymmetry introduced by these anharmonic terms, especially the cubic term, that causes the average distance between atoms to increase slightly as they vibrate with larger amplitudes at higher temperatures.
Ah, so it's an imperfection in the forces that leads to expansion.
Exactly. The everyday phenomenon of thermal expansion is the direct consequence of the anharmonic nature of the lattice potential. Without anharmonicity, things wouldn't expand when heated.
And phonons aren't just linked to expansion, they are the main way heat actually travels, especially in insulators and semiconductors. Heat flow is basically a net drift of this phonon gas from hot to cold regions. Metals have electrons helping out too, but phonons can still carry a significant chunk of the heat, maybe 1 to 40%. The simple kinetic theory picture for thermal conductivity, kappa, involves specific heat, CV, average group velocity, VG, and the phonon mean free path, L, how far a phonon travels before scattering, roughly phi 13 CV VGL. So high conductivity means you need lots of heat capacity, fast phonons, and crucially, a long mean free path. They need to travel far without crashing.
Right. And this brings in harmonicity back into the picture in a critical way. Imagine that perfectly harmonic crystal again. Phonons wouldn't scatter off each other at all. The mean free path would only be limited by the physical size of the crystal itself. Thermal conductivity would be enormous, almost infinite theoretically.
But real materials have resistance to heat flow.
Exactly. And what limits the mean free path intrinsically? It's phonon-phonon scattering, which is only possible because of that very same anharmonicity in the lattice potential. These anharmonic terms allow phonons to interact, to collide, merge, decay. This limits how far they can travel. So here's the fascinating insight. The same anharmonic imperfection that causes thermal expansion is also the fundamental reason why even a perfect crystal has finite thermal conductivity, or thermal resistance. Without it, insulators would be almost perfect heat conductors.
Okay, so if heat gets stuck because phonons scatter, let's dig into those scattering mechanisms. You mentioned phonon scattering as the intrinsic one, driven by anharmonicity. Traditionally, people focused on 3 phonon processes, 2 combine into 1, or 1 splits into 2. But our sources mention 4 phonon scattering can be surprisingly important.
Yes, that's become clearer more recently, especially at higher temperatures. 4 phonon processes were often neglected, but in some materials, like the high thermal conductivity semiconductor boron arsenide, Calculations show that including 4-phonon scattering significantly reduced the predicted conductivity, bringing it much closer to the experimental value from maybe 2000 down to 1400 WMK. So it can be really quite significant.
And within these phonon collisions, there's this really crucial distinction between normal N processes and umclap U processes. This seems critical for thermal resistance.
It absolutely is. It's a subtle but profound difference. In normal processes, the total crystal momentum of the interacting phonons is conserved. Think of it like K1 plus K2 equals K3. All the wave vectors stay within that first Brillouin zone. N processes redistribute energy among the phonon modes, but they don't actually degrade the total momentum flux carrying the heat. So by themselves, they don't cause thermal resistance.
Okay, so N processes just shuffle things around. What about umclap? That sounds more dramatic.
It is. Kehlklacken comes from the German for to flip over. In these processes, the total crystal momentum is not conserved in the simple sense. What happens is the sum of the initial wave vectors, K1 plus K2, mathematically falls outside the first Brillouin zone. Because of the lattice periodicity, this gets mapped back into the first Brillouin zone by subtracting a reciprocal lattice vector, G. So it looks like K1 plus K2 equals K3 plus G.
So the momentum effectively gets flipped back.
Exactly. And that flip, represented by adding or subtracting G, signifies a major change in the direction of momentum flow. It effectively degrades the total momentum flux carrying the heat. Clap processes are the dominant mechanism for intrinsic thermal resistance in crystals. They're the main reason heat flow isn't infinite. They become important mainly at higher temperatures, maybe above 1/3 of the Debye temperature, when you have enough high-energy, large KOK phonons populated near the zone boundaries to make these G-vector processes likely. And importantly, umclap scattering is a direct consequence of the discrete, periodic nature of the crystal lattice. It wouldn't happen in a continuous medium.
Beyond phonons hitting each other, there's also the interaction between electrons and phonons. That sounds fundamental.
Oh, it's hugely fundamental. The electron-phonon coupling is arguably one of the most important interactions in all of condensed matter physics. It governs so much. For instance, electrical resistivity in metals. Why does resistance go up with temperature? Because the vibrating lattice, the phonons, act as scattering centers for the conduction electrons. More heat means more vigorous vibrations, more phonons, more scattering events for the electrons trying to flow, higher resistance. But here's where it gets really beautiful and maybe counterintuitive. This same interaction is the key to conventional superconductivity.
Wait, scattering causes resistance, but it also causes superconductivity. How does that work?
It seems paradoxical, right? But think about it this way. Normally, electrons repel each other, Coulomb repulsion. But in a deformable lattice, an electron moving through can slightly distort the lattice around it, pulling the positive ions closer. This creates a region of slight positive charge excess, a sort of wake of virtual phonons. A second electron coming along later can be attracted to this positively charged distortion left by the first electron. Under the right conditions, this phonon-mediated attraction can actually overcome the direct Coulomb repulsion for electrons near the Fermi surface.
And they pair up.
Exactly. They form Cooper pairs. These pairs behave like bosons and can condense into a single coherent quantum state where they flow without any resistance. That's the essence of the Bardeen-Cooper-Schrieffer BCS theory. The definitive proof that phonons were involved was the isotope effect. Changing the mass of the ions in the lattice, by using different isotopes, changed the superconducting transition temperature, T-city, in exactly the way predicted if lattice vibrations were mediating the pairing. Later, Amygdala-Lyberg theory refined this for stronger coupling.
Okay, so we have intrinsic scattering, phonon-phonon, electron-phonon. But what about imperfections? Any deviation from that perfect crystal lattice must also scatter phonons, right?
Absolutely. These are extrinsic mechanisms, and they become particularly dominant at low temperatures where umclap scattering freezes out. Any break in the perfect periodicity is a problem for phonon transport. You have point defects, things like impurity atoms, different isotopes which scatter based on mass difference, vacancies, missing atoms, interstitials, extra atoms squeezed in. These tend to scatter high-frequency phonons effectively. Then there are dislocations, which are like lines of defects running through the crystal. These are better at scattering lower-frequency phonons. In polycrystalline materials, the grain boundaries between the different crystal domains are like walls that scatter phonons of all frequencies quite strongly. And in nanostructures, thin films, nanowires, the physical boundaries or surfaces of the material itself can become the most important scattering mechanism, drastically reducing the mean free path in thermal conductivity. How rough the surface is matters a lot, specular versus diffuse scattering.
So you add up all these scattering sources.
Pretty much. Matheson's rule is a simple approximation saying the total scattering rate, which is like 1 over the mean free path or lifetime, is the sum of the rates from all independent sources. Unclap, defects, boundaries, electron-phonon, etc. One total, it's each one U plus one defect plus B tiers. It gives us a framework for understanding and even engineering thermal conductivity by controlling these defects.
This is all fascinating theory, but it raises a big question. How do we actually see these tiny elusive phonons? How do we measure those dispersion relations we keep talking about? Experimental proof is key.
Exactly. We need ways to experimentally probe these vibrations to validate the models and understand real materials.
One major set of tools uses inelastic light scattering. The basic idea is simple. Shine photons, light, onto the material, and some photons will scatter off phonons, exchanging energy and momentum in the process. If the scattered photon has less energy, lower frequency, it means it created a phonon, Stokes scattering. If it has more energy, higher frequency, it absorbed or annihilated a phonon, anti-Stokes scattering. The energy shift tells you the phonon energy.
Right. And there are different flavors. Raman scattering typically uses visible or near IR light. It's primarily sensitive to optical phonons, usually right near the Brillouin zone center, because photons don't carry much momentum compared to phonons. Raman is great for identifying specific vibrational modes, like a chemical fingerprint, and determining crystal symmetry. It requires the vibration to change the material's polarizability.
Okay, so Roman for optical modes. What about Brillouin scattering?
Brillouin scattering also uses visible light, but it probes the low-frequency acoustic phonons, again near the zone center. It's essentially light diffracting off the periodic density fluctuations created by the sound waves, phonons. It's very useful for measuring elastic constants and the speed of sound directly. There's also a nonlinear version, stimulated Brillouin scattering, SBS, used with intense lasers.
So light scattering is good for the zone center, but to map the entire dispersion curve across the whole Brillouin zone, you need something else.
That's where inelastic neutron scattering, INS, and inelastic X-ray scattering, IXS, come in. They are the workhorses for getting the full picture. The key is that the probe particles, thermal neutrons, or high-energy X-rays, have wavelengths comparable to interatomic spacings and energies comparable to phonon energies. This means they carry enough momentum to probe phonons anywhere in the Brillouin zone, not just near the center.
Let's start with neutrons. INS sounds like the classic technique.
For decades, INS has really been the definitive technique. You use thermal neutrons from a reactor or spallation source. Their energies are in the MeV range, wavelengths and angstroms perfect match for lattice vibrations. By measuring the energy lost or gained by the neutron and the angle it scatters at, you can precisely determine the energy and momentum of the phonon involved. You can map out the entire soup dispersion, get phonon lifetimes, even information about the atomic motions, eigenvectors. The main limitation. Neutron scattering requires pretty large single crystal samples, usually several cubic millimeters or even cubic centimeters, which just aren't available for many interesting new materials.
So sample size is the bottleneck. What about IXS then?
IXS is a more modern technique, really enabled by powerful synchrotron X-ray sources. It uses very high-energy X-rays at keV range, detecting the tiny energy shifts, mech scale, caused by phonons scattering against that huge incident. Energy is technically challenging, but achievable with specialized spectrometers. Like INS, it can map the full dispersion relation for all phonons across the entire Brillouin zone.
And the big advantage?
Sample size. IXS can be performed on extremely small samples, micrograms of powder, or single crystals just tens of micrometers across. This is a huge deal for studying novel materials, synthesized only in tiny quantities. Plus, X-rays don't interact strongly with electron spins, so IXS is great for studying phonons in magnetic materials without getting confused by magnetic excitations, magnons, which can be an issue for neutrons.
So it sounds like there's no single best technique. They're complementary tools in the toolbox.
Exactly. Raman and Brillouin are accessible lab techniques, great for zone center modes and specific applications. INS is the gold standard for the complete picture if you have large enough samples. IXS is fantastic for overcoming the sample size limitation for new and complex materials. The choice really depends strategically on what you want to measure and what kind of sample you actually have.
This leads us nicely into the final part, moving beyond just observing phonons to actually controlling them, this whole field of phononics.
Yes, if we connect this to the bigger picture, there's been a real shift. We've gone from using phonons to explain material properties to actively trying to design and control how phonons behave and transport energy. That's the essence of phononics. It's about engineering heat and sound flow, much like photonics engineers light, enabling new technologies in areas like thermal management, energy conversion. maybe even quantum information processing.
And a key tool here seems to be the phononic crystal, or PNC. What are these?
Think of them as artificial materials where you deliberately create a periodic pattern in the acoustic properties, say, the density or the speed of sound. It could be a periodic array of holes drilled in a membrane, or pillars etched on a surface, or different materials layered periodically. This periodic structure fundamentally changes how phonons can propagate through the material.
How so? What effects do they have?
Two main things. First, they can create phononic band gaps. These are frequency ranges where no phonon modes are allowed to exist or propagate through the structure, just like electronic band gaps for electrons in semiconductors. This allows you to build things like acoustic filters, mirrors, or waveguides for sound and heat. Second, the periodic structure can significantly alter the phonon dispersion curves, often making them much flatter. Remember, flatter dispersion means lower group velocity, Vg equals to keck. Slower phonons mean less efficient heat transport.
So PNCs can basically block or slow down heat flow.
Exactly. They can dramatically reduce the lattice thermal conductivity. This happens through both coherent effects, the band gap formation, and group velocity reduction, which rely on the wave nature of phonons interacting with the periodic structure and incoherent effects. The interfaces of all those holes or pillars act as very effective scattering centers, just like grain boundaries or defects, further reducing the phonon mean-free path. The combined result can be quite striking. People have shown you can use nanostructuring to make crystalline silicon, normally a good thermal conductor, have a thermal conductivity lower than amorphous silicon while still keeping its good electronic properties.
Wow. So what are the potential applications for this kind of heat control?
One big area is thermoelectrics. Remember that electron crystal? Phonon glass is ideal. Good electrical conductor, bad thermal conductor. Phonon engineering, using nanostructuring or PNCs as a prime strategy to slash the thermal conductivity without hurting the electrical conductivity too much. This directly boosts the thermoelectric figure of merit, ZT, which determines device efficiency.
Makes sense. What else?
Heat dissipation in electronics is another huge one. Getting heat out of tiny, powerful chips is a major challenge. Phononics could offer solutions like highly efficient directional heat spreaders, or conversely, ultra-effective thermal insulators to shield sensitive parts. People are looking at things like patterning 2D materials like MODAS2 to guide heat anisotropically in stacked 3D circuits.
That actual cooling devices.
Right, solid-state cooling using the Peltier effect and thermoelectric coolers.
Yeah.
Companies like Phononic are already commercializing this for demanding applications like cooling electronics in data centers, for AI hardware, even potentially replacing conventional HVAC systems eventually. Again, the efficiency hinges on improving that ZT value through material science, heavily involving phonon engineering.
And you mentioned quantum information.
Yeah, that's more forward-looking, but people are exploring using individual quantized phonons as quantum bits, qubits, or using them as a quantum bus to connect and transfer information between other types of qubits, like superconducting circuits. Phononic cavities could trap and manipulate single phonons for these quantum applications.
So this whole shift from just observing to actively designing really opens up a massive playground for innovation.
It really does. If you step back and look at the journey, the phonon started out almost a century ago as a theoretical concept needed to solve a puzzle in thermodynamics, the specific heat problem. And now, it's become absolutely central to condensed matter physics. We understand it as the quantum of lattice vibration, the carrier of heat and sound, a key factor in electrical resistance, and even the mediator of conventional superconductivity. We've explored its fingerprint, the dispersion relation, the difference between acoustic and optical modes, and how that crucial imperfection and harmonicity is responsible for both thermal expansion and thermal resistance. And experimentally, we've gone from early hints to sophisticated tools like Raman, Brillouin, INS, and IXS that give us these incredibly detailed windows into the phonon world.
So wrapping this all up, what does this mean for you, the listener, and where is this heading? Clearly, the shift towards phononics means we're entering an era where we can engineer the thermal and acoustic properties of materials with unprecedented control. But, as our sources suggest, challenges remain. Accurately predicting thermal conductivity from first principles, especially accounting for those tricky higher-order scattering effects like 4-phonon processes, is still an active research area. The hunt for a higher temperature, maybe even room temperature, superconductors often involves searching for materials with optimized, strong electron-phonon coupling. and practically. Taking these amazing phononic crystal concepts from the lab and figuring out how to manufacture them cheaply and integrate them reliably into large-scale devices is a major engineering hurdle. And then there's the whole quantum frontier. Can we truly harness the quantum nature of individual phonons for future computing and sensing technologies? Just amazing, isn't it? The phonon, once this abstract theoretical idea, is now becoming a tangible engineering tool, a tiny quantum ripple shaping tomorrow's technology. It's been quite a journey. What aspects of this will you delve into next?